Okay, so we talked previously about solute, solvent, and then why things are soluble and why things are insoluble. We talked about the solvation process, and we said that like when an ionic compound is thrown into water, that the water is able to separate those ions, even to a small extent. So all ionic compounds are at least slightly soluble. We gave defined solubility. So we said if it has a group 1 metal in it, if it has ammonium, if it has nitrate, if it has acetate, it's soluble. And then everything else we can consider insoluble, because those are the things that we really have to memorize for the AP Chem test. All right, so then we consider everything else insoluble, unless it tells you otherwise. Right? Soluble ionic compounds are strong electrolytes. Insoluble ionic compounds are weak electrolytes. And then polar covalent compounds, and we haven't gone back over what polar is or how to predict it yet, but polar covalent compounds, then they're soluble, but they are non-electrolytes because they don't break up into ions. We said that all we're doing is we're breaking the intermolecular forces that occur between the molecules. Right? And again, we are going to talk about intermolecular forces, how to predict them, and stuff like that later on as well. So I know that we've used some terms that we haven't accurately defined, but we'll get around to it. Today, all I want to talk about are precipitation reactions. With that, we're going to talk about double replacement reactions, which is what a precipitation reaction is basically. It's also called a metathesis reaction. And I think that's it. We'll see. And then I also want to talk about net ionic equations. So those are the two things that we're going to talk about today. Precipitation reactions and net ionic equations. Let me prepare my work surface. All right. Hello. So a precipitation reaction is going to happen whenever you mix two aqueous solutions. So you can see there lead 2 nitrate, that's aqueous because it has the nitrate. All nitrates are soluble. Potassium iodide, the potassium is the group 1 metal, so it's always soluble. But then when we mix them, we end up getting a solid, and then the other is aqueous. So let's take a look at this. Why is this solid? Well, it's lead 2 plus, which is not a group 1 metal, it's not ammonium, and then it's iodide. Okay, iodide is not nitrate, iodide is not acetate. So that's why it ends up being a solid, because it is insoluble. We can say that the force of attraction between the lead ion and the iodide ion is much stronger than the energy that the water has to separate those two particles. Now, it is an ionic compound, right? It is made between a cation and an anion, so it is slightly soluble. But it's not 100% soluble. We have this idea of solubility. You know, that's how much of a substance at a given temperature will actually dissolve. And we'll talk more about solubility in Chapter 17 when we talk about KSP. Okay, solubility products, things that are slightly soluble. We'll do some of those calculations in detail. Then here's the threshold. The threshold is anything where we have less than 0.01 molar, that's considered insoluble. And we already talked about which solubility guidelines we need to memorize. Okay, we have that down in our notes already. So let's talk about whether these compounds are soluble or insoluble. Sodium carbonate, Na2CO3. Is that going to be soluble or insoluble? What? Soluble. Why? Because what? Group 1 metal, thank you. Then what about lead 2 sulfate? PbSO4. Soluble or insoluble? Yeah, insoluble. Now this would be a good explain question, and I mentioned this before, the difference between explain and justify on the AP Chemistry exam. Justify is when you have to support your answer with data. So let's say that you did a calculation earlier, then it asked you about that calculation. You would use that calculation to justify your answer, or maybe there's actually data that's given in the question. That's justifying. To explain is almost just given the definition, right? So if this said lead 2 sulfate is insoluble, explain why would be the statement. And so the explanation would be it does not contain a group 1 metal ion, ammonium ion, acetate, or nitrate. Therefore, it is insoluble. So that's just saying this is why, right? It's almost just a definition. And as we go further on, we'll have situations where it's justify, okay? And I'll point those out. So don't worry about memorizing this. We don't do that anymore. If you want to, go ahead. But I think you're almost always given a solubility chart, even in college, at least your first year. Exchange, that's the other one. So let's do some practice of these double replacement reactions. All right. A lot of the reactions that we run into are just double replacement reactions. So let's try this with barium chloride and potassium sulfate. So it says, predict the identity of the precipitate that forms when aqueous solutions of barium chloride and potassium sulfate are mixed. So let's write the whole reaction. So we've got barium chloride, BaCl2. That tells you it's a solution. Now, according to our solubility guidelines, that would be insoluble, right? But it tells us that it's a solution. So we forget about our guidelines at that point, and we call it aqueous because it tells us specifically it's a solution. So there's barium chloride, and then there's potassium sulfate. The first question is, predict the identity of the precipitate. So before we write the chemical reaction, let's see if we can predict the identity of it. You have 3 options for your products, right? So this is a double replacement reaction. Your first option for your products are barium chloride and potassium sulfate. So in other words, what we're saying is barium chloride mixed with potassium sulfate forms barium chloride and potassium sulfate, right? So if that were true, would it actually be a chemical reaction? No. So that's not a chemical reaction. So is that a good possibility for the answers, for the products? No. Okay. The second option is for the barium to get with the potassium and the chloride to get with the sulfate. Is that a good option? No. Why not? Yeah. Barium's a positive ion, potassium's a positive ion. Chloride's a negative ion, sulfate's a negative ion. Right? So a cation is not going to get with a cation, anion is not going to get with an anion. So the third option is the switching places. Barium hooking up with the sulfate and potassium hooking up with the chloride. Is that a good option? Yeah, that's a good option. That shows an actual chemical reaction. Right? So what's going to be the precipitate? Is the potassium getting together with the chloride going to be the precipitate, or the barium getting together with the sulfate? The barium with the sulfate, right? Because we know that potassium is a group 1 metal. Any group 1 metal is going to be soluble, right? So really for letter A here, the identity of the solid would be barium sulfate. What's the charge on barium? Yeah, 2+. What's the charge on sulfate? Minus 2. So what would be the formula for barium and sulfate? Yeah, BaSO4. Always remember it's according to their charges, nothing else. So that would be the actual answer to letter A. Barium sulfate is the identity of the precipitate. And then in letter B, they're asking us to actually write out the chemical reaction. And I started to do that, but I need some more space here. I know that you guys can't necessarily do this, but I'm just going to move this dude down a little bit. Okay. And so what we're going to see, first of all, it's going to be a one-way arrow. Right? So in other words, the reaction is going to go to completion. We're going to have basically products left over. We said the barium is going to get with the sulfate. And then we said that the potassium is going to get with the chloride. So let's get the potassium and chloride first. What's the charge on a potassium ion? +1. What's the charge of a chloride ion? -1. So what's the formula if potassium and chloride get together? Yeah, it's just KCl, right? Now, is that going to be solid, liquid, gas, or aqueous? Aqueous. That thing dissolves. Okay. And then we already said what the formula for barium sulfate was. It's BaSO4. Is that going to be solid, liquid, gaseous, or aqueous? Solid. Is it balanced? No. So let's balance it. What do I put where? Right. Now is it balanced? Yeah. So now it's balanced. Very good. Very good. Any questions on that? Yes?
If it was like SO4, like 2, would the 2 be moved to like would it transfer to, or would it stay with the SO4?
Well, let's do one. Okay. Except, yeah, we'll do one. So let's say it's aluminum sulfate, which is Al2SO4 3, not exactly what you were looking for, but all right. And let's just pretend that that's going to be aqueous, okay? Let me check my actual solubility rules here. Sulfates, yeah, so that aluminum sulfate would actually be aqueous. And let's mix that with a lead-2 nitrate. Is that right? Let's see. Yeah, that'll work. So let's mix that with lead-2 nitrate. Okay. So again, this is going to be a double replacement reaction. So we've got a one-way arrow. So the aluminum is going to get with the nitrate. The lead is going to get with the sulfate. Right? So what's the charge on aluminum? Yeah, aluminum is usually a +3. And what's the charge on a nitrate? -1, right? So when they get together, how many aluminums, how many nitrates? Yeah, 1 aluminum, 3 nitrates, right? And that's going to be solid, liquid, gaseous, or aqueous? That's going to be aqueous because of the nitrate, right? Aqueous because of the nitrate. And then the other one is going to be lead getting with the sulfate. What's the charge of a lead, of this lead? Yeah, this one's +2 because it's lead-2 nitrate. What's the charge of sulfate? -2. So how many leads and how many sulfates? 1 lead and 1 sulfate, right? Solid, liquid, gas, or aqueous? Solid in this case. And then we just got to balance it. So I'm going to put a 2 in front of this and a 3 in front of there. And that's going to balance the nitrates. They each have 6 now. And then I think I'm just going to put a 3 in front of here. And I should be in good shape. Any questions? Does that answer your question, Lauren? All right. So then let's talk about the next part and we'll be done. And that is writing a net ionic equation. It's actually simpler than what the instructions tell you. It's just basically you break everything up into ions that can be broken up into ions, cross out what appears on both sides, bring down what's left over. All right, let's try it for the sample exercise 4.4 here. Write the net ionic equation for the precipitation reaction that occurs when aqueous solutions of calcium chloride and sodium carbonate are mixed. Okay, why don't we start out with first, go ahead and you jot down the reactants. Okay, write down the formula of the reactants, and then we'll compare scores here. Here's what I have. You need more time? I know. Do you need more time or you got it? You got it? Okay. So here's what I have for my reactants. Now go ahead and predict the products. I'm going to freeze it again. Freeze ray. Freeze ray. And predict the solid. I feel like an old man here. I can't get this to unfreeze. Damn remote's broke again. How'd you do? Yay? Nay? Okay. So that's going to be what's referred to as the complete molecular equation. So your normal chemical reaction, that's your molecular equation, all right? To make it a net ionic, first thing you want to do is split everything up into its ions. So anything that's aqueous, break up into the ions that make up that compound. Solid, liquid, gas, you leave it alone. So for instance, this calcium chloride is going to become calcium ion. Ions have to be aqueous. And then 2 chloride ions. Sodium carbonate's aqueous, so I'm going to have 2 sodium ions. Oops. Aqueous. Plus the carbonate ion. Again, anything that's aqueous, I'm just breaking it up into its ions. Calcium carbonate, that's a solid. So I don't break that dude up. Sodium chloride's aqueous, so I break that up. I get 2 sodium ions because there's a 2 in front of it. And 2 chloride ions because there's a 2 in front of it. Now, if you ever get to this point and you got an ion on the left-hand side and then an ion on the right-hand side and they're not the same, like number of them, you probably did something wrong. This is what's called a complete ionic equation. Okay, basically everything that is ionic in aqueous is broken up. But what we want is the net ionic equation, and for that we just cross out what appears on both sides. So here's the calcium ion. Notice on the product side there is no calcium ion. So I keep that. I keep that calcium ion. I got 2 chlorides as reactants, 2 chlorides as products, so I cross those out. I've got 2 sodium ions as a reactant, 2 sodium ions as a product. I cross that out. And then my carbonate does not appear on both sides. So I keep that. And that yields calcium carbonate, CaCO3 solid. So that's going to be my net ionic equation. And the net ionic equation shows you only what's reacting. So a net ionic equation can be useful when you just want to know like how much precipitate do I form or something like that. Everything that we crossed out is called a spectator ion. So there's my symbol for anything that's crossed out. Those are the spectator ions. The other ions don't have a specific name. So, all right. Any questions? Do you want to try one on your own? And then I'll cut you loose? Yeah, just one? Maybe a short one? Let's try this one. We'll do a simple one. Okay, so take that, and write the equation, so the complete molecular equation, then write the net ionic equation. And we'll compare answers. What time do we get out of here? Huh? Here's my answer. All right, so you're good to go if you need some more help. I'll give you some more help. Now on the worksheet that you have, you can now do number 6. All right, number 6 on the back of the first page. That's some more practice on this right here. Yep.